Okay, so it is our great pleasure to welcome Professor Gal Shmuel from the Technion in Israel. He's an expert, a world expert on elastodynamic metamaterials, and he has just been granted a prestigious ERC consolidator grant. And today, Gal is going to talk on non-Hermitian elastodynamics without gain and loss. Gal, the floor is yours.
Thank you, Sebastian, for the kind introduction. So the title speaks for itself. I'm going to talk about non-Hermitian elastodynamics without gain and loss. And this is an excellent platform to maybe advertise the grant that is related to that, the ERC consolidator grant, where I have openings for PhD and postdoc students. And the broad idea is to create, model, and use non-hermiticity in elastodynamics in order to develop metamaterials, to discover new phenomena that are related to wave propagation in continuum solids. And maybe I will head toward the bulk of the talk, and I will just want to make a brief background and start with non-Hermitian quantum mechanics. So basically, the term hermiticity corresponds to some mathematical symmetry, a mathematical symmetry that ensures real eigenvalues and orthogonal eigenvectors for certain operators. And this is one of the postulates in classical quantum mechanics, because they want the observables, whatever they measure, to be a real quantity. And hence, in traditional quantum mechanics, the operator, in their context, the Hamiltonian, is a real quantity. In 1998, Bender and Bocher posed the question, can we get real eigenvalues without having a Hermitian operator? And the answer is yes. They build what now is known as a parity-time symmetric operator, which provides real eigenvalues even if the operator itself does not satisfy the hermiticity condition. And the key point is that this type of operator provides real eigenvalues until it don't. In what sense? In the sense that there is a measure of non-hermiticity where when this measure of non-hermiticity exceeds a certain thresholds, the eigenvalues become complex. And this transition point is called the exceptional point. So what we are seeing here, we are seeing an example that was illustrated in Alu's review paper in Science, where we have some typical two-level system or a system with 2 degrees of freedom, where there is a certain parameter of the system that governs, that measures the non-hermiticity. Let us call it, in this case, gamma 1. Below a certain value of this parameter, we have what is called an exact PT symmetry, meaning we have 2 real eigenvalues. Now, if we associate these eigenvalues with, let's say, the natural frequencies of the system, then this means that the frequencies are real. It corresponds to wave propagation, non-decaying mode, non-increasing mode, and that's it. Beyond a critical value, this realness of the spectrum is broken, and we get complex eigenvalues, or in this case, 2 imaginary eigenvalues which correspond to an enhancement or decaying in the frequencies and the corresponding wave. Now, these singularities are a source of numerous counterintuitive phenomena, which I will demonstrate soon. But before that, I would like to add a little bit more of theoretical background. So what we see here, the left side of the illustration, is actually a section from a higher dimensional space where we have two parameters, and there these curves are extended to a surface that is called a Riemann surface. And this Riemann surface has some neat features that I will also discuss later on. And this is one of the hallmarks of an exceptional point. An exceptional point is a point on a surface that is called a Riemann surface, as we are seeing here. Another difference between Hermitian operators and non-Hermitian operators is the fact that while for Hermitian operators, the natural modes or eigenvectors are orthogonal one to another, for non-Hermitian operators, this no longer holds, meaning that the natural modes are actually they are no longer orthogonal. They have some projection one on the another, which means that if you tune the system, you can get a degeneracy. So what do I mean by a degeneracy? I mean two eigenvalues, two eigenmodes that become one. And this is what we see here in this illustration. So if we want to think about the natural modes of the system as some vectors, if you will, then these vectors become one. And this degeneracy is a source of many counterintuitive phenomena, which, like I said, I will demonstrate soon. And at the exceptional point, not only the eigenvectors coalesce, but also the eigenvalues. Okay, so that was in the context of quantum mechanics. This is where it started. And in 2007, Christodoulidis' group translated these concepts from quantum mechanics to optics. And they translated what was referred to PT symmetry to an optical gain and loss, meaning injection and extraction of energy from the system, which in optics come naturally with the use of lasers, and which means this PT condition translates to a certain distribution of the refractive index in the medium, meaning that its real part is distributed symmetrically, while its imaginary part is distributed antisymmetrically. And once we have that, we can get all kinds of special phenomena. For instance, if we have a grating that satisfies this condition, at the exceptional point of the scattering matrix, we can get unidirectional transmission, perfect unidirectional transmission, meaning a wave that comes from the left will propagate with one transmission coefficient to the right without any reflection, whereas from the opposite side, we will have some reflection. This concept was also exploited by Alu's group to realize negative refraction, and it is also useful to develop super-sensitive devices because the splitting of the natural frequencies near the exceptional point follows a square root law, in contrast with the splitting of the frequencies near regular singularities. So this idea of PT symmetry in optics was actually acknowledged by Nature as one of the top 10 discoveries in its decade. And it was later on disseminated to mechanics. So what we see here are two examples. In the left, we see another example from Alu's group, where they realized unidirectional invisibility of sound propagation for acoustic waves using two loudspeakers, where in the right-hand side, we see a conceptual implementation of PT symmetry to realize negative refraction of flexural glaze by a source group. The challenge in realizing PT symmetry in solids is the generation of gain. While in optics, it comes naturally with the availability of lasers, in mechanics, it's not so simple, and there are different approaches to do that. So theoretically, Christiansen's group suggested to employ the acoustoelectric effect in piezoelectric semiconductors. Another approach that was realized experimentally was using shunted piezoelectric elements, and this was done by Rutzene's group, and you can see also the works of Wang, Asor, and Sigaras. Now we come to the contribution of my group, and I would like to pose the following question. Can we tailor non-Hermitian phenomena like we saw earlier, meaning exceptional points, negative refraction, and so on, in elastodynamics without gain and loss? And the answer is yes. And the reason is the unique tensorial nature of elastodynamics. This will be explained soon. The starting point is, first of all, to change our perception of space for those exceptional points, for those non-Hermitian operators. The PT symmetry is for the frequencies, meaning if we let, for example, examine the wave equation in 1D for a solid, if we look at this equation, whenever the stiffness mu and the mass density rho is real, omega square will always be real. We cannot avoid this. Whenever we don't have any gain and loss for rho and mu, the frequencies will always be real. And this is similar for optics, for the electromagnetic waves with the refractive index. This indeed corresponds to energy conservation and the fact that the waves are not decaying in time or in space. What we do here, what we will do soon, is to reformulate the problem. We won't look at the operator that delivers the natural frequencies, but we will look at the operator that generates or dictates the wave numbers, which are the reciprocal quantity for the wavelengths. And this can be complex even when the material properties are real, even when we don't have any energy gain or loss to our system. So symbolically, we look, instead of looking at determining the frequency for a given wave number, we will determine the wave number for a given real frequency, which physically corresponds to different types of problems. Where comes the uniqueness of elastodynamics in what we will show later on? In order to do that, in order in some way transfer energy between some modes, we will exploit what exists only in elastodynamics, and this is the coupling and the coexistence of both transverse and longitudinal waves, transverse and longitudinal modes. So shear waves, where the displacement is perpendicular to the direction of propagation. This is like light, right? In electromagnetics, the electric field is perpendicular to the propagation, where the pressure waves are longitudinal modes, and these are like sound. And in elasticity, they both coexist. And their coexistence and coupling can allow us to mimic gain and loss without really having gain and loss in the system. And in order to show that, I will examine the simplest problem that these two modes are coupled. And this is the ancient problem of in-plane waves in a periodic elastic isotropic layers. So what we will look at? We will look at periodic repetition of, as the title says, elastic isotropic materials, and we will characterize the natural modes of this system. And this was done long time ago and was done again and again and again. But here I will show that exceptional points exist and that these exceptional points give rise to anomalous wave propagation. So maybe I'll just give a quick review of the governing equations. So again, elastodynamics, so we have the stress sigma, which is given by the constitutive relation, the elasticity tensor C times the strain. This is what we have here. We have the balance of linear momentum, and the material properties are periodic. So let's say the Lamé constant, the shear modulus, and the mass density, they are periodic with some periodicity H. And this gives rise to essentially two coupled partial differential equations with periodic coefficients. How do we solve the problem? There are different ways to do that. Again, this is all well known, but I'll just summarize it briefly. So one approach is to look at each layer to find a basis for a solution, which is determined from the solutions of an infinite medium, a bulk, and then use this basis as or a linear combination of it in order to satisfy certain boundary conditions, because we don't have a bulk, we have actually a finite sample, right? what are the continuity conditions? So we actually have the same vertical wave number, right? The continuity which is denoted by K2. And we have the continuity of the displacement and the normal components and the shear component of the stress. And these together constitute what we call a state vector, right? So we have the continuity of the state vector across the interfaces. And we can show that the state vector across a unit cell is related to a certain matrix. And this matrix is denoted by T. And this T depends on the properties of the layers, the frequency, and the vertical wave number. How do we proceed from here? So the solution, since the system is periodic, the solution must have the form of a Bloch-Floquet solution, meaning we have some periodic function with the periodicity of our lattice or laminate times this phase shift. This equation, together with the previous one, delivers us a dispersion relation that relates the properties of the laminate, the frequency, and the macroscopic or effective, if you will, Bloch wave number. Okay, so now we can connect what we have here to what we had at the beginning. Instead of talking about an operator that gives us the evolution in time, that delivers us the frequencies of the system, now we have an operator that delivers us the wave numbers, or if you will, the reciprocal to the wavelength, the macroscopic wavelength, this KB, which is a function of our system, and if we want to prescribe a real frequency. And this operator T is non-Hermitian. Why? Because it's non-Hermitian. It's complex and not symmetric, and it doesn't satisfy the symmetries that are related to hermiticity, which means two things. First, it delivers us complex eigenvalues. And this is genuine complex eigenvalues, not only imaginary or real, in contrast with the electromagnetic problem, which if we will have time and the people here will have interest, I can address later. And secondly, the natural modes that it delivers are non-orthogonal, meaning that we can tune the system and make them coalesce and achieve an exceptional point, which I will show you soon. This is again from, let's say, an analytical analysis of the system. But let us demonstrate it with some numerical examples. So the numerical example that I'm going to consider is a laminate that is given by the following properties. And this laminate was considered earlier by Willis and MetaMAT's for their own interest. And these properties are given here. And now I evaluate the dispersion relation, the frequency versus the KB, the Bloch wave number, for a given value, prescribed value of vertical wave number. And this is how the spectrum looks like. So what do we see here? So this is the irreducible first Brillouin zone. So like I said, we actually have, so the transfer matrix is actually a 4x4. We have a symmetry that corresponds to forward and backward waves. So I can look only on the irreducible Brillouin zone. I can look only on those with, let's say, positive KB. So the continuous curves correspond to the real part, and the dashed curves correspond to the imaginary part. And here, near this frequency, we see indeed an exceptional point. What do we have? We have two branches, like we saw at the beginning in the illustration from a loose paper. So we have here two real branches with some finite KB and zero imaginary parts. So these are two propagating modes. We have real wave number, and here they coalesce. The real value become the same value, and beyond that point, we have an increase in the imaginary part. So this is an exceptional point. We have a degeneracy in the spectrum of our system, and not only the eigenvalues coalesce, that is the Bloch wave numbers, but also, as it should be in exceptional point, the modes coalesce too. The system is degenerate. Instead of having these two, for instance, distributions of the mode shapes and, for instance, the normal stress, the two modes become one, okay? And as we saw at the beginning, now we have the Riemann surface, these fancy surfaces, in the wave vector space. So far, traditionally, or the bulk of the work so far was for the frequencies as the eigenvalue in a space that was for, let's say, the coupling between the degrees of freedom in the system and the gain or the loss. Here we don't have any gain or loss. The system now is controlled by, if you will, the vertical wave number. And the output or the eigenvalues of this operator is the horizontal, the effective horizontal wave number, right? Instead of having omega versus gain, we have KB versus K2, mathematically, okay? And all this, like I said, without any gain and loss. We can do some further analysis and we can look at some sections of these surfaces. And what we see here, we see different frequencies where we fix KB. Later on, I will explain why I do that. And I evaluate the values of KB versus different values or versus function of K2. This is what we get, okay? This is like sections of the surfaces that we showed earlier. Why am I doing this? I'm doing this because now I can have a different perspective for the exceptional point that we saw. Earlier, we saw it in the diagram of the frequency versus KB, and here we see the same exceptional points where we have KB versus K2. And later on, I will go back to these plots because I need to, okay? Let us proceed. Okay, so what this has to do with anomalous wave propagation. So I first want to recall that the energy is given by, or the propagation of energy is given by what we call the acoustic pointing vector, which can be written in the following way, like the real part of the product of the stress times the velocity. And these angular brackets denote an averaging over one temporal cycle and our unit cell. So Willis showed, it was actually showed even earlier, but he did it in a nice way, that the energy propagates like the derivative of the frequency with respect to the wave vector for propagating mode. This is proportional to that. Meaning that the sign of this depends on the sign of this. Now, next to the exceptional points, we have the splitting, meaning that near the exceptional points, we have curves with opposite slope, meaning one of them can refract negatively if it can be excited, okay? So if we want to think about the angle of propagation, it is actually given by the ratio between the components of this macroscopic pointing vector, energy flow, group velocity, if you will, because this is the group velocity, and it is the derivative of the omega with respect to KB over the derivative of omega with respect to K. So like I said, near the exceptional points, the slopes are of opposite sign, and hence we can get negative refraction. So I want to go back and think of, and I want to associate the analysis of this modal problem of this periodic laminate with a particular problem where we truncate this infinite periodic medium with some half space. So this is how we're going to excite the system. I'm going to associate, again, the modal problem with some boundary value problem. So if we think about an anti-plane shear problem, not the in-plane shear, meaning that the displacements are, let's say, outside and inside of this image, then the energy flow at each point looks like this expression, meaning that the energy flow in the x2 direction and the phase velocity in the two direction, because this goes like K2, and the macroscopic energy flow in the x2 direction will all have the same sign, right? We cannot have, let's say, negative K2 and a positive P2, or the average of P2. And this is why in this, I will call it canonical setting, you cannot get negative refraction for antiplane shear waves, which is identical mathematically to electromagnetic waves. By contrast, the x2 component of the acoustic of the Poynting vector looks like this, meaning that the average of this quantity can be of opposite sign with K2 and with its averaging over the unit cell. And this is what we'll show soon. In other words, the vertical phase velocity and the macroscopic groove velocity can be anti-parallel, allowing us for negative refraction. And simply put, we can have an excitation from this half space. We're gonna have positive P1 because energy comes from the left, it must go to the right. But along the x2 direction, the energy will head to the negative side. So let's solve this problem analytically. We are considering some incident wave from this half space, and its corresponding fields can be derived from this type of potential according to the equation that we have below. This incident wave excites two Bloch modes in this medium. And these Bloch modes are determined from the diagrams that we saw earlier. We have two Bloch modes. We have the KB is being extracted from what we saw earlier. And in order to determine the amplitudes, we have to satisfy here the continuity condition. It's basically a simple problem, the continuity of the displacements and the sigma 2,1 and sigma 1,1. So we have, if you will, a 4x4 problem. We have two reflection coefficients to determine, and we have two transmission coefficients to determine for the two Bloch modes. Let's plug numbers. So let us assume that the half space is given by the following properties. Let's take this angle of incident to incident wave. Why am I choosing this angle of incident wave? Because this angle at this frequency corresponds to this value of the vertical wave number. Again, if you want to think about basically what's going on here, by setting up the properties of the half space and the angle, we actually dictate the vertical wave number, right? We actually dictate the wavelength in the x2 direction. And now this is the diagram that tells us what is the relation between the Bloch wave number and the vertical wave number. And we can see that we have here two modes. These are the modes that are associated with this TM. One of them is propagating because it's purely real, and the other is evanescent. It is decaying. And just as a sanity check, we have this equation for the balance of energy. And so we have that the energy of the incident waves and the energy of the reflected and transmitted waves, they all sum up to 1, as it should. And now we will see that indeed, near the exceptional point, we have a branch, and this is actually this branch that leads to negative refraction. So what we have in the left simulation is a conventional refraction. We have a positive refraction in the angle that is not associated with what we've just showed. And in the right-hand side, we see the simulation that corresponds to the calculation that I've just showed, where indeed we achieve negative refraction. So I'd like to emphasize that we just saw a realization of exceptional points and, for instance, negative refraction without any gain and loss, using the fact that in elastodynamics we have two modes, and these modes are coupled, and spatially this coupling through the periodic repetition of these interfaces mimics gain and loss. Okay. For completeness, I will just note that we can think about, in some sense, the dual problem, where we connect the homogeneous half space to the laminate in the direction of the layering. So what this system corresponds to it corresponds to a case where we enforce KB. So in the previous problem where we had the canonical scattering problem, we actually enforce K2. We actually enforce the continuity of K2, so the medium, and here we enforce KB. Here the problem is much more complicated because there isn't really a natural compatibility between what's going on in the laminate and the half space. So this type of excitation will generate an infinite number of evanescent modes to tailor the continuity condition across the boundary. And actually using this configuration, Willis in 2015 and Srivastava in 2016 realized negative refraction for antiplane shear waves. Okay, so I have these details on how we can solve this problem. It's somewhat technical, so I will skip it. It is less interesting. And I will skip to the second, before I skip into this short second part of the talk, I would like to thank my excellent students, Ben Lustig, Guy Elbaz, and Alan Moafra, and my colleagues, Professor Nimrod Mosev, Alexei Malebaev, and Ankit Srivastava, and our fundings. And these are the references to the relevant works. I have a bonus that I can show in a couple of slides that I couldn't resist of introducing in this platform. So I call it generalized Willis materials. So what are Willis materials? In conventional elastodynamics, we have the following constitutive relations between the stress and the linear momentum to the strain and the velocity. So we have the stiffness, if you will, and the mass density. And Willis has shown that effectively, for the average fields or macroscopic fields, the effective stress actually depends also on the velocity, and the momentum actually depends also on the strain. And this gives rise, or is being characterized by the so-called Willis couplings. These are these S's. And in the long wavelength, these S's correspond to asymmetry in the medium. So here we see a realization of this concept by Alus group from 2019, where they looked at a beam and they broke the symmetry of the unit cell, as we can see here, and they measure the corresponding Willis coupling. So my takeaway from this slide is that this S is being generated by asymmetry. And we actually had an excellent talk by Andre Alu in this MetaMAT's series on what broken symmetries give rise to for metamaterials. But I would actually want to note that there is some analogy, an earlier analogy to cross-couplings that emerge from broken asymmetry in nature. And this is actually piezoelectricity. Piezoelectricity couples the mechanical and the electrical fields. So here sigma is the stress again, D is the electric displacement field, grad phi is the electric field. So the stress actually depends on the electric field in piezoelectric materials through the piezoelectric tensor, if you will, this B. And the electric displacement field depends on the strain, again, through the piezoelectric tensor, here denoted again by B. And this happens when on the atomic level we have some broken symmetry, where we do not have a crystal with centrosymmetric structure, as we can see here. So when we break the symmetry at the atomic level, we get electromechanical coupling. So what happens when we combine these two? Okay, when we combine these two physics, when we combine elastodynamics and piezoelectricity in an asymmetric way, we find new couplings. And so this is actually a work that I did with my postdoc, René Turner-Salomon, I think in 2020 or 2019, where by generalizing the approach of Willis for homogenization, we showed that macroscopically, in addition to the Willis coupling, the electric displacement field also depends on the velocity, through what we chose to write as W. and that the momentum depends on the electric field, what we call W dagger, if you will. So symbolically, without going through the mathematical hell that we went through in order to show this, let's say this emergence comes naturally when we look at this matrix representation, right? So these cross-couplings, like the Willis couplings, they capture anisotropy in the impedance and the scattering properties, and like Haberman and Alu showed in the context of Willis coupling, is that these generalized couplings are also necessary in obtaining a macroscopic description, a homogeneous description that respects physical restrictions such as reciprocity and energy conservation and passivity and causality. Sorry. And I would like to note that this idea, while I demonstrated it here for piezoelectric materials, it can also be applied to different materials that have other types of coupled physics. For example, piezomagnetic materials or thermoelastic materials. And in those cases, instead of the electric displacement field and the electric field, we will replace them with the corresponding physical quantities. For instance, the magnetic field and magnetic induction in piezomagnetic materials. So the acknowledgement here goes to my former excellent postdoc René, my students Alan Muafra and Mike Kozda, and my colleagues Mike Haberman and Dinoris Daniel Torrent, and with whom I had 2 papers that I like. These are the 2 papers in the special issue of wave motion in honor of Willis, and Graham Milton, from whom I learned a lot, and I had many fruitful discussions. So I told Bogdan it's going to be 40 minutes. Yeah, it took 40 minutes, not too long. I'll be happy to take any questions. If any.
Excellent, Gal. Super talk. So please, people, come forward and ask your questions. I'm sure there are many, many questions.